Hey everyone! So we've encountered a lot of isomers in organic chemistry. There seems to be a lot of confusion because isomers come in different kinds and forms. So this particular video will be dedicated to identifying what isomers are, what are the different kinds of isomers, and some examples so that hopefully when you study on your own, find them on the internet and look through your text, you'll know what the different kinds are and it'll be easy for you to differentiate between each. So let's dive in. The word isomer is of Greek origin, from the root words isos and meros. If you translate those two words to English, they literally mean equal and parts. Technically, isomers are compounds which have the same formula but different structures. They're made of the same atoms connected differently or represented differently in 3D. For example, I have C6H14 as my molecular formula, and I represent it here as N-hexane. I can represent N-hexane in 3D with something that's called a Newman projection. But this is not the only 3D configuration for N-hexane. Similarly, C6H14 can be represented as a different molecule. This is called 3-methylpentane. They have the same molecular formula as N-hexane, and they are isomers of one another. Isomers can be classified into different things. The first classification is called a constitutional isomer, from the root word constitute, made up of. Constitutional isomers are made up of the same atoms that are connected differently. Same atoms, different connectivity. Constitutional isomers have subcategories, the first of which is called the skeletal constitutional isomer. Skeletal meaning that they have different carbon skeletons. From the previous slide's example, I have the molecular formula C6H14, and I have isomers such as N-hexane or 3-methylpentane. I can rearrange this into something that's like 2-methylpentane or 2,2-dimethylbutane and still have the same molecular formula. So, as long as I have the same atoms, just connected differently, those are skeletal constitutional isomers. The next kind of constitutional isomers are called functional constitutional isomers. Functional meaning functional groups. I can have a molecular formula of C3H8O that could pertain to something that's an alcohol or an ether. And the last kind of constitutional isomer is called the positional constitutional isomer. I have the same functional group positioned differently in my particular molecule. So, if I take my C3H8O and generate an alcohol, I can generate either a terminal alcohol or a secondary alcohol, all of which are constitutional isomers. The next kind of isomers are called stereoisomers. Stereo, Greek, ster, solid, 3D. Stereoisomers are compounds whose atoms are connected in the same order but differ in three-dimensional structure. Normally, if we look at the line 1 structure of methane, we think of it as something that's 2D. We forget that carbon is actually a tetrahedral center that exists in 3D. It's better for us to represent it with the wedges and dashes to remember that there is a 3D configuration for your carbon centers. And this is very important because of the 3D configuration, we can generate different kinds of stereoisomers. Similar to constitutional isomers, stereoisomers have subcategories as well. The first subcategory of stereoisomers are called conformers or conformational isomers. Conformational isomers have different arrangements of atoms resulting from bond rotation. Let's take, for example, N-hexane. We can look at the bond between carbon 3 and 4 and draw them in these things that are called Newman projections. Recall that sigma bonds are cylindrically symmetrical, meaning that I can rotate those particular bonds freely. I can't isolate conformational isomers like I can do with constitutional isomers. Constitutional isomers have different properties because they have different molecules altogether. Conformational isomers pertain to the same molecule but have different resulting arrangements in 3D because of bond rotation. Both the conformational isomers you see on the screen are Newman projections of N-hexane. And since they interconvert rapidly, you can't easily isolate them from one another. Think of it as if they were snapshots of N-hexane mid-shifting position. Conformational isomers can also be represented in different ways. Not only can you use Newman projections as representations, but there's this less known, less used representation called your Sohor's projection. The next kind of stereoisomers are called enantiomers, from the Greek word enantio, meaning opposite. Enantiomers are molecules that are mirror images of one another but are not identical. Enantiomers are like your left and right hand. Your left and right hand are mirror images of one another. They're very similar, but if you try to superimpose them, they're not completely superimposable with one another. If I take a molecule such as this, draw an imaginary mirror between it, and draw the exact mirror image of it, you'll realize that these mirror images are very similar but are not identical. I can't superimpose them, and they have different absolute configurations. Absolute configurations will be covered in a different video. So let's just focus on the identity of enantiomers, which are molecules that are mirror images but are not identical to one another. The last kind of stereoisomers I'll be discussing are called diastereomers. Diastereomers are stereoisomers that are not mirror images of one another and are not superimposable. Enantiomers are like your left and right hand. Diastereomers are like your right hand compared to the right hand of somebody else. Pretty similar, but a lot of differences. We have different kinds of diastereomers, and some examples are already shown on your screen. Basically, if you have more than one chirality center, you can generate diastereomers that are non-superimposable, non-identical, and non-mirror images of one another. Cis-strand stereoisomers are actually classified under diastereomers. The prefixes cis and trans are of Latin origin. The prefix cis means on the side of, while the prefix trans means across from or on the other side of. Cis-trans diastereomers have the same order of substituent connectivity but differ in spatial orientation of the atoms. In the right, you will see examples of 1,3-dimethyl cyclohexane, but on the left is something that is a cis 1,3-dimethyl cyclohexane, and on the right is a trans 1,3-dimethyl cyclohexane. Cis-trans diastereomerism are consequences of the rigidity of a particular molecule. In the case of cycloalkanes, I can't just freely rotate it because I'm going to end up breaking some bonds. This is also actually true for alkenes, which you'll learn about later on. So alkenes can also have cis-trans diastereomerism. Note that I can't just flip over a molecule and generate a trans molecule just by doing that. For you to be able to either generate a cis or a trans diastereomer of something, you have to break one of the bonds and connect them to the opposite face. The next kind of diastereomers are called configurational diastereomers. Basically, in some textbooks, those are your regular diastereomers. Configurational diastereomers are stereoisomers that have opposite configurations at some chirality centers. Technically, the definition of non-mirror images, non-superimposable, actually refer to configurational diastereomers. In this particular example, we're looking at 2-amino-3-hydroxybutanoic acid. On the left, you have a 2R and a 3R configuration, and on the right, you have a 2R and a 3S configuration. No matter how much I rotate the bottom carbon, you're not going to generate the same configuration for the right molecule. They are of opposite configurations at some, one or more chirality centers, but the same configuration at the others. They're not mirror images. Notice that the top carbons are actually identical to one another. So, configurational diastereomers normally only happen if you have two or more chirality centers. Technically, if enantiomers are your left and your right hand, your configurational diastereomers are like the right hand of you and your friend. The last kind of diastereomer that I'm going to be discussing are called epimers. Epimers are actually a special kind of configurational diastereomers. They're special because they are only differing at one particular chirality center, but all the other chirality centers, if you're comparing two molecules, should be the same. I have here the structure of D-glucose and D-mannose, and they only differ in the highlighted chirality centers. Technically, epimers show up if you have three or more chirality centers for your diastereomers or for your molecules. All in all, those are the different categories and subcategories of isomers. This particular slide summarizes the relationship and the differences between each kind. I hope this particular video helped you identify what isomers are and help you define and differentiate between each kind. In the next videos, we'll be focusing more on assigning absolute configurations so you can distinguish between stereoisomers and some key definitions relating to the stereoisomers and the tetrahedral centers of the carbon. So that's it for this particular video. Thank you, and I hope you have a good day.